Volkov on Vortons and their stability. To you, Mikhail.
Okay, thanks. First of all, thank the organizers for inviting me. And this talk is presents. We heard already the talk of Richard Bati, and here I will present, if you will, complementary viewpoint. So everything is based on a series of published papers in collaboration with Eugene Radu and Julian Garo. Julian is, by the way, here in the audience, and also on some work on preparation. And so, first of all, a little bit of history of how we constructed modern solutions. And okay. And how we started addressability. First of all, the story started about 30 years ago. The cosmic strings. It's essentially a theory which is very exposed with a direct interaction between the two scalars. And the parameters of the theory are adjusted in such a way that in the vacuum, the first U1 is broken, whereas another U1 is unbroken. And so the theory possesses solutions which are essentially the Abrikosov-Nielsen-Wolitsin vortices containing in the core the condensate of the second complex scalar field. And the condensate is charged, and so therefore there could be electric current, and so this gives rise to superconducting strings. And if one considers this theory as a part of some grand unification theory, then one discovers that the current along the strings is really gigantic. It's huge. It has astronomical values of something like 10 to the 20 ampere. And when people discovered this, well, everybody was surprised, and the people invented many interesting applications for this in the cosmological context. And this morning we already heard something about, but maybe it's better to talk to specialists. Next, some years later, an important generalization was suggested. The idea was this. So if you look at the superconducting string from far away, you can forget about its internal structure, and you can treat it as a sort of elastic rope of which carries a current and momentum. And then if you cut a finite piece of this rope and then glue the ends, then the momentum will be running in circle, creating angular momentum. And so the resulting loop will be stable against contraction, in the sense that it will want to minimize the energy, but the centrifugal force will prevent it from contracting to zero. And so presumably, people thought this should lead to formation of a stationary object called Vorton. Well, and again, everybody was interested, and people invented many interesting applications. In particular, even there were papers where people wanted to consider these Vortons as seeds of galaxies. Well, and the story like that continued for about 20 years. But when we looked into the problem some years ago, we discovered, to our great surprise, that there were no explicit solutions. People always used this phenomenological macroscopic description, and nobody cared about resolving underlying equations of the field theory. But you know, in field theory, many things can happen. Maybe this is stable against contraction, but it can break in pieces, it can bend, it can radiate away, and many things, really. In particular, we were anxious about the following process. If there is a Vorton, and if something is running in a circle, then nothing forbids this system to radiate away its energy. And when we screened the literature, the only thing we could find some stationary solutions in non-relativistic systems, but they do not radiate simply because there is no radiation in non-relativistic case. And also in relativistic systems, there were some solutions, numerical solutions, but they were manifestly non-stationary. And so that's why we wanted to integrate to find really solutions. And so we consider the global version of Vortons model. Essentially, if you switch off the vectors, you end up with a theory which contains two complex scalars, phi and sigma, and there is a potential, interaction potential between the two scalars. And then, in the simplest case, one looks for solutions with axial symmetry, stationary solutions with axial symmetry, which means that the first scalar is there is an ansatz where the scalar depends only on rho and z of coordinates of cylindrical coordinates, whereas the second scalar, in addition, carries a phase which can depend on time and on phi, on azimuthal angle, but the energy momentum tensor does not depend neither on t nor on phi. And this ansatz gives rise to the following conserved quantities: to the charge q and angular momentum g. And the ratio of g over q is an integer winding number, which can sometimes be called spin. So next we took this ansatz and put it into equations of motion, and this gives us the following system of elliptic differential equations. So if solution exists, it guarantees that the Vorton is stationary. But it was not obvious at all that solution existed. So we were looking for solutions with the usual regularity requirements, but the most difficult part was the winding, because we wanted the solution to be of toroidal shape, and torus have two generators, one like that and the other one like that. And the phase of the first scalar should wind around this generator, which is automatically encoded in this ansatz, whereas the phase of the second scalar should wind over here, which is not simple, because the phase should wind in a rho z plane around the point whose position is a priori unknown. Yeah, and so this was difficult, and we spent around about a year trying to integrate these differential equations, and at some point we were absolutely convinced that the stationary solutions did not exist. But then Eugene Rado arrived, and then he was able to find solution for in about 6 weeks of hard numerical work, and he got a convergence, and finally these were his solutions, and this gives structures, toroidal structures, and with the correct winding, if you take this cross section of the torus, we see that the phase winds around this point, whose position is the outcome of the numerical analysis. Well, and so, if you will, this gave us Vorton solutions for the first time 20 years after they were proposed by Davis and Scheller. Yeah. Next, here are some properties of these solutions. So the ansatz contains frequency omega here, this one, and it can be viewed as a parameter of the solutions. So if you change omega, then the energy and the charge change, and we discover that the charge has a minimal value, and there are two branches, and it is expected that the stability of the solutions should change at this point. And in particular, if you trace the energy against Q, then there are two branches, and for the upper branch, there are solutions for whom the ratio of E over Q is larger than for free particles. Therefore, for these solutions, it's energetically favorable to disintegrate into free quanta. Whereas for the lower branch, solutions cannot disintegrate because the ratio is lower than this. So then we published, but we didn't publish just these solutions. We managed to write a whole physics reports on all related solutions in field theory about knots and Vortons, and this could be. It was 4 years ago, and it could be interesting for people in the audience because it's exactly about the subject of our conference. So here is roughly the content of our physics reports. So let me use one minute. So we considered static solutions in Faddeev-Hopf model first, stabilized by Hopf charge. Next, we considered anomalous solitons, also static, stabilized by Chern-Simons number, non-abelian rings. Then the issue of angular momentum for stationary soliton. Then spinning solutions, spinning cuboles, spinning skyrmions, spinning monopole and antimonopole pairs, Vortons. And next, non-relativistic systems, Vortons in the Bose-Einstein condensates, spinning light bullets in nonlinear optics, and then moving rings in the Bose-Einstein condensates and in ferromagnetics. So it could be, I think, interesting for people. Well, and from this list, I will only mention these solutions in the B condensates because many people in the audience are solid-state physicists. So the point is this: let's take our relativistic Vorton solution, and then if you have it, one can multiply these fields phi and sigma by some time-dependent phase factors. And this gives a solution of Gross-Petoevsky equation. It's just, if you will, a coincidence maybe. So, in other words, any Vorton can be embedded into non-relativistic system. And one can also proceed in other direction. And in this, we used the old result of Batty, Cooper, and Sutcliffe, who managed to construct the solution of Gross-Petoevsky in the case where two order parameters satisfy the following constraint. And when we uplift this to Witten's model, we obtain solution in the so-called sigma model limit with the following constraints. And for us, it was important because it gave us the initial guess at constructing the solution. Well, next also we have solution with the gauge fields included. And then there is the important issue of stability. Well, a year after our paper was published, Batty and Sutcliffe published their paper on three-dimensional simulations. And well, here is the picture from their paper. They managed to first to construct stationary solutions, but they were more interested in the solutions which are thin rings, whereas our solutions are thick. So they wanted them to be thin, and when they did the full 3+1 dimensional simulations, they discovered that the solutions are unstable with respect to bending and pinching, so it decays. Okay, so at first it was a little bit discouraging for us, but then we went on, and then we first of all we wanted to analyze the stability of strings. After all, Vortons are made of strings. So we considered two particular models of course we considered also the Witten strings, but also more physical models, other models, semi-local string and Weinberg-Salam string. In both cases, there are cylindrically symmetric solutions like this rod with electric current, and in particular in the Weinberg-Salam case, it's interesting because the current has the typical values of billions of amperes. And so this is real physics, irrespective to any Vortons. So this should describe some processes, some discharge processes in electroweak plasma. So we call these solutions electroweak thunderbolts. And then we did the full stability analysis of these solutions, linear stability analysis. So we analyzed the spectrum of fluctuation operator, and then we discovered that the solutions had unstable modes. Of course, they are unstable. But what is interesting, that the wavelength of all unstable modes is always larger than certain minimal value. And this reminds of Plateau-Rayleigh instability in hydrodynamics. It's a well-known thing. So if you look at the water tap, at the water jet in the kitchen, you will see that first several centimeters are smooth, and then ripples start because the instability sets in. Well, and then the point is that since the instability cannot be very short, one can eliminate instability simply by imposing periodic boundary conditions with sufficiently short period. And then this, well, one can do it first mathematically and then physically. Suppose that we bend a short vortex and close it. Well, of course, when you bend it, there could be some new instabilities arising. But still, this is suggestive. And so we understood that small and thick, sufficiently small and sufficiently thick vortex loops might be stable simply because they're hard to pinch and hard to bend. It's this. And finally, we did the full dynamical simulations, and this is this is basically this is Julian who was driving this. So one considers the full hyperbolic problem in a finite spatial box with reflecting boundary conditions, and one starts from exact Vorton solution. But then, due to discretization error, some non-trivial dynamics arises, and we discovered that the result crucially depends on value of m. If m is large, then the Vortons are thin and large and unstable. If m is small, they are fat and they become stable. Sorry. So here is the movie. Oops. So it's m equals to 6. And you see almost immediately it integrates, disintegrates into pieces. So they are bound to stay in the box because of the reflection, but they are not spinning. They have spin equals to 0. Yeah. So now it's m equals to 3, and now the cross section of the shown and these arrows are the current. You see, it also breaks. Yeah. Okay, and then m equals to 1, and in this case nothing happens, just nothing. And Julian integrated on so for many weeks, so many weeks of runtime. The unstable solutions that they break within, I don't know, 10 minutes, and this stays like that, just moving slowly in the box. Nothing happens simply because you see it's too fat to be pinched and too fat to be bent. Yeah. Okay, so this I can stop. Nothing interesting will happen. Next. So how to stop it? No. So wait. Not include. Yeah. So finally, we conjecture. Well, the evidence is that Vortons with the lowest spin and with large enough Q seems to be stable. And what is interesting, we found a confirmation of this conjecture in the theory of Q-balls. Q-balls is a simple theory with only one scalar field, and they exist in two versions: in relativistic version, in a non-relativistic version. And in the second case, they described optical pulses in a nonlinear medium. And then there are stationary solutions with angular momentum. And then there is a group, optical group, who really who did a great job. They analyzed, they did a full stability analysis at the linear and non-linear level, exactly with the same conclusion as ours. So sufficiently fat, broad donuts with a small hole in the center, they say are non-linear stable for m equals to 1. So this is their conclusion. And finally, these are my conclusions. And so we presented the numerical solutions for Vortons, stationary spinning vortex loops. They're characterized by energy, charge, and angular momentum. And they cannot disintegrate into free particles because of this reason. However, they typically break into smaller pieces which do not spin. But nevertheless, there is a parameter region for the smallest value of spin and for large enough charge, in which case the solutions seem to be stable in the full 3+1 dynamical nonlinear evolution. Well, and this could lead, I presume, to some interesting applications. Okay, thanks.
Thank you very much. Questions, please. I have actually curiosity because you mentioned the analogy with elastic ropes, etc. I wonder if there is a regime between fat and thin, whereas you have a writhing instability or a kink instability, like you have in flux.
Of course. So
Can you? Yeah, sorry.
if they're not fat, anything is possible. All sorts of instability. They can break it. You know, you saw the video, and so they simply they're unstable. They're definitely unstable. So they're
Okay.
Okay.
Okay. Thank you.
Thanks.